Good morning. So we start our lecture, and I continue the discussion of Lorentz transformations in the context of the Dirac equation. But before we start, let me ask if you have questions concerning what has been considered in the previous lectures. Okay, if you don't have questions, then we continue. So what we have done last time, we arrived at the following formula. S minus 1 gamma nu S. Let's write it in this way. Gamma mu maybe this formula. S gamma mu S minus 1 is equal to eta mu nu gamma nu. And so this is equation which we have to solve and find the matrix S, which performs the transformation of wave function psi in such a way that the transformed Dirac equation has the same form as an original one. And we found out that if we consider for a Lorentz transformation a one-parametric subgroup given by exponential epsilon, where epsilon is infinitesimal parameter of this transformation, multiplied with the matrix nu omega, where nu omega has components mu nu given by the formula eta mu rho omega rho nu. Then for matrix S, the corresponding formula for Lorentz transformation, turns into the following equation. So here is not lambda, here is not eta lambda. Turns into the following equation: S minus 1 depending also on epsilon, gamma mu S depending on epsilon, equals to lambda mu nu depending on epsilon, gamma nu. And as the next step, we take this equation, differentiate it with respect to epsilon, introduce a quantity which is x given by d s over d epsilon s minus 1, and such that this equation for x takes the form gamma mu x is equal to eta mu rho omega rho nu gamma nu. And this is an equation which we have to solve for this matrix X. And the convenient way is to solve it is to look for a solution in the following form. X is taken as some matrix lambda with components with elements rho lambda multiplied by omega rho lambda. So we look for a solution which is linear in generators omega, and omega, I recall, these are generators of Lorentz transformations. They carry indices rho and lambda, and this is the way how this is a form in which we are looking the expression for matrix S, for matrix X. So substituting this into this formula, then we obtain an equation of the following form: gamma mu lambda rho, say with indices rho lambda little, minus lambda rho lambda omega gamma mu equals to 1/2 eta mu rho gamma lambda minus eta mu lambda gamma rho. So I canceled on both sides omega, and I use the fact that since omega is skew symmetric, so omega rho lambda is equal to minus omega lambda rho, we can also take lambda to be skew symmetric. So in other words, to satisfy the condition of this type. With this assumption, equation for lambda rho can be solved. This equation for this matrix can be solved, and I will give directly the solution right away. So it's lambda mu is 1/8 gamma mu gamma nu, and here I put square brackets, meaning that I'm considering the commutator of this matrices. So this is the same as 1/8 gamma nu minus gamma nu gamma mu, which is due to the Clifford algebra, can also be written as 1/4 simply as a product gamma nu, where index mu is not equal to nu. Well, this is explicitly taken into account by this symmetrization or anti-symmetrization procedure, and therefore, well, you can check that this is solution by explicitly substituting this matrix into the equation above and using the Clifford algebra relation for gamma matrices. Then you can check that this is indeed so. This is a solution. And on the other hand, since we found it, we see that our equation for S can be now specified as follows. So we had ds over d epsilon equals to x multiplied with s. But now we found what x is. We said that this is 1/4 gamma mu omega mu nu multiplied with s. And this is an explicit differential equation, which is essentially, the right-hand side is a product of a matrix, 4x4 matrix, because gamma nu is a 4x4 matrix. Multiply with matrix S is equal to derivative ds over d epsilon. And this equation must be supplemented with the initial condition. Initial condition is telling us that if we consider a trivial transformation, so in fact, transformation corresponding to identity, in other words, we take epsilon to be equal to 0, this means that, so epsilon is equal to 0, then it means we don't do anything, and then the corresponding matrix S must be simply equal to the identity matrix. So this differential equation, together with this initial condition, has a unique solution. And this unique solution, as you can see, is simply given by exponential of the matrix 1/4 gamma nu omega mu nu. Now, and multiply with epsilon. So if you differentiate this expression with respect to epsilon, then this matrix 1/4 gamma mu nu omega mu nu comes down, and exponential remains exponential after differentiation, so it gives you s back, and you get exactly the differential equation above. So what is written down here is a solution. Epsilon is a one parametric subgroup, so epsilon is any real number here. Originally, we took it small in order to consider expansion around epsilon is equal to 0. But in general, epsilon is a real number, so you can fix it, for instance, to be equal to 1. So in this way, you just get rid of it. Or another way to say is that you absorb it in omega. And then the final form of the corresponding transformation S is taken as exponential 1/4 gamma mu nu omega mu nu, which you can also write due to the skew symmetry of the matrix omega, or of this tensor with two indices omega, in the following form. You can say that this is the same as 1/2 sum over mu is less than nu, gamma mu, gamma nu, omega mu nu. So this is the formula for the Lorentz transformation of our spinor, which we wanted to find. So this is the final expression. So this means that under the Lorentz transformation lambda from the proper orthochronous Lorentz group, our Dirac spinor transforms in the following way. So psi prime on x prime, where x prime is obtained from x by means of Lorentz transformation with the element lambda, is given by exponential 1/4. Let me write explicitly sum from 0 mu and nu running from 0 up to 3 gamma mu gamma nu omega mu nu multiplied or acting on a function psi on x. So this is how our spinor must transform under Lorentz transformations in order for the wave function psi prime on x prime to satisfy the Dirac equation in the new or transformed Lorentz frame. So the answer we found is rather interesting. The first thing we can notice is that the matrices lambda mu nu, which feature in these Lorentz transformations, these matrices lambda, they satisfy the following algebraic relation, which is the commutator of two matrices, say lambda mu nu and lambda rho sigma. If we just commute them, we find that the commutator, due to the Clifford algebra relations, can be written in the following form: eta nu rho lambda mu sigma minus eta mu rho lambda nu sigma minus eta nu sigma lambda mu rho plus eta mu sigma lambda nu rho. In fact, looking at this expression, you recognize that this is nothing else but the commutation relation between generators of the Lie algebra of the Lorentz group. So this generators lambda, these matrices lambda, are nothing else as generators of the Lie algebra of the Lorentz group. And this means that we obtained exactly what we have discussed last time, namely that the Lorentz transformations we have constructed are transformations realizing the spinor representation of the Lorentz group. So what we have obtained is a spinor representation, or spinor, because our transformations act on these 4 component objects, which we call spinors. And so in this way, we can say that what we have constructed is a spinor representation of the Lorentz group. And it's important to realize that this representation is different from the vector representation, or yes, from the vector representation that is given, the latter is given by the matrices lambda mu nu, matrices lambda mu nu, which we have used in order to transform components of the vector x mu, realizing, let's say this is different. Let me write explicitly that this representation is different from the vector representation acting on coordinates x mu, acting with the help of lambda mu nu. Okay, before I continue with the properties of this interesting new realization of the Lorentz group, let me ask if you have some questions concerning the derivation.
Professor, can you explain how we use this lambda mu nu? One question.
How we used?
Use lambda mu nu in our Dirac question.
Lambda mu nu, where they are sitting here. They are sitting in this transformation. So lambda mu nu, what we have done, we have found that lambda mu nu has the following form: 1/4 gamma nu. And these are infinitesimal, what we have found that these are infinitesimal generators of the Lorentz group, or it's the same as generators of the Lie algebra of the Lorentz group. And if you have a Lorentz transformation, say given by this matrix lambda mu nu, then we know that this transformation is constructed with the help of the infinitesimal generators omega mu nu, which are skew symmetric. And now if we take these generators omega mu nu and combine them with the matrices lambda mu nu, which are in fact given by this antisymmetric combination of the gamma matrices, and construct such an object, such a matrix given by exponential of gamma mu nu, omega mu nu, then the matrix S, which is obtained in this way, will be realizing the spinor representation of the Lorentz group. And spinor representation is a representation which tells us how spinor transforms under Lorentz transformations. So with this matrix psi prime on x prime, so the wave function in the new Lorentz frame is obtained from the wave function in the old Lorentz frame by means of this transformation S, matrix S, acting on the spinor, old spinor, or spinor in the original Lorentz frame. And this is a way how this matrix S, Y matrix S, is a generator or is an element of the Lorentz group, but now realized in terms of 4x4 matrices acting on components of our spinor, such that Dirac equation remains covariant. Okay, so matrix S or matrix lambda, it does not enter the Dirac equation itself. The Dirac equation is an equation which we have seen last time. So this is what is this? This is just a second. This is equation I gamma mu d mu minus m psi on x is equal to 0. This is our Dirac equation. And the point is that if you perform on our spinor S this transformation with on our spinor psi with transformation with matrix S, then in the new frame equation will look the same, provided we just put primes on x's and a function psi. This is how it will look like in a new frame, provided S satisfies, provided S is given by this expression here. Okay, so this is what we have achieved.
Yes.
Does this answer your question?
Yes, understood.
Yeah. So we achieved our goal. We build up explicit realization of the Lorentz transformation. In other words, we understood how function psi must transform under Lorentz transformation for the Dirac equation to remain covariant, to look the same up to this relabeling of x to x prime and psi to psi prime, how it must look in the new frame. Now, let us investigate this Lorentz transformation we found in more detail. And what we can do, we can first specify this transformation for the case of spatial rotations. So let's specify this transformation for spatial rotations. No, this means that I'm considered just rotations. So Lorentz boosts we consider later. And we know that the usual three-dimensional rotations, they can be specified by given a rotation axis, and this can be done by specifying the unit vector n with components ni, I running from 1, 2, 3. And unit means that if you compute the length of this vector, then the length is equal to 1. So this is rotation axis, the axis around which we will be rotating. And we need to specify rotation angle. And rotation angle I denote by theta. So theta will be my rotation angle. So in other words, an axis, which is specified by this unit vector. And I need also to specify an angle, theta, by means of which I rotate. Then elements omega ij, which I need then to express where n and theta, these elements omega are then given by the following expression. So this is minus theta rotation angle multiplied with epsilon I j k multiplied with nk. So this is the infinitesimal matrix of such a transformation. And then what you can do is you can compute gamma I, gamma j, multiply with omega ij. This gives you minus theta gamma I, gamma j, epsilon I, j, k, and k. And this sometimes people write in the following way. They specify this as minus theta. So this expression here, gamma ij epsilon ijk, sometimes people write as minus 2i sigma k. So because I'm summing over indices I and j, then I get an expression which depends only on index k. And so the resulting expression is this then is, in fact, it becomes, in this case, plus 2i theta, 2i theta, sigma k and k, where this sigma, if you write them with upper indices, you might see that due to their Clifford algebra relations of gammas, that this can be written also in the following form. This is gamma 5, our fifth gamma matrix, gamma 0, gamma I. It's just the way to rewrite the same expression here with upper index. You can show that due to the Clifford algebra relation, this is the same as an expression I'm given here in terms of this gamma 5, gamma 0, gamma I. And you see also that the object we have introduced is a matrix. And this matrix has three components. And so to speak, it is the collection of three matrices labeled by this index I. You can say that this is collection of sigma 1, sigma 2, and sigma 3. Yes, collection of three matrices. And in this way, you can identify it with a matrix 3 vector. So to write it in this way. And in fact, you can now see that if you take ji to be equal to 1/2 sigma I, which is according to relativistic convention on raising and lowering indices, is the same as minus 1/2 sigma I, then these j's satisfies the following algebraic relation. If you take a commutator of ji jj with jj, then the result will be minus I epsilon I jk jk. And if you look at this expression here, you recognize that this algebraic relation is nothing else as the Lie algebraic relations of the generators of angular momentum, right? Algebraic relations of angular momentum is the same as algebra of angular momentum. And on the other hand, you know that this is commutation relation for angular momentum is nothing else as relations of the generators of the Lie algebra of the rotation group. So Lie algebra of the rotation group. So you take this matrices ji, perform this commutator, you see that this algebraic relation is satisfied, and then in this way you see that what you have realized is that you realized the algebraic relations of the Lie algebra of the rotation group. And in this way, you can naturally interpret these operators ji as spin operators. So sigmas or j's, whatever you prefer, you can call them spin operators. Spin operators. And so these objects are related to the notion of spin. And the notion of spin comes from characterizing the transformation properties of your object say vector, spinor, scalar, with respect to three-dimensional rotations. So spin is a property of your wave function to transform in a certain way under three-dimensional rotations, under rotations of space. And therefore,
Professor,
yeah.
sorry to interrupt. Is theta over here infinitesimal rotation?
Sigma I is a generator of infinitesimal rotation. And in this way, when you say infinitesimal generator, that means that this is a Lie algebra generator of the Lie algebra of the corresponding rotation group. So these objects Ji, they are generators of the Lie algebra. So this relation here is a Lie algebra relation. So this is Lie algebra of the rotation group. And the rotation group is nothing as SO3. So what you see here is the Lie algebraic relations between the generators of the Lie algebra SO3. I should write it with a little S and a little O. And this is a Lie algebra of the rotation group, which is SO capital, S capital, O capital 3. So special orthogonal transformations. Special orthogonal transformations realized by elements of the group SO3. And this is the same as we know, this is the same as rotation group or group of rotations. Group of rotations coincide with SO3. So this is a group of orthogonal matrices satisfying their condition of a unit determinant. So all matrices have unit determinant. And now what we see here is that we realize these special orthogonal transformations at the level of the Lie algebra by 4x4 matrices Ji, which we construct via gamma matrices. So the objects which we see here are realized in terms of 4x4 matrices. But what we are realizing is, in fact, the rotation group SO3, or its Lie algebra SO little 3. Okay? That is what we are doing here.
Yeah, fine.
Now, the rotation by finite angle, if you consider not infinitesimal, but you rotate by finite angle theta, then we have to use the general formula we found for such a transformation. So we have to take S as an exponent of this general formula we have to use here. But here our indices mu and nu are taking only values 1, 2, and 3. So we restrict ourselves here to indices 1, 2, and 3 to sum up. And then what we have is in terms of matrix sigma capital can be written as I over 2 sigma vector multiplied with vector n and multiplied with the rotation angle theta. This is how this expression will look like in terms of this matrix sigma capital. Now explicitly you can see why it is so. So you start from here from say 1 over 2 gamma I j omega I j multiply with theta. Then you substitute here realization of omega ij by this explicit expression, which involves the Levi-Civita tensor. Then you use the definition of sigma capital. And at the end of the day, then this is an expression which you have here. And sigmas are 4x4 matrices, and so you can actually continue and compute this exponential explicitly in the usual way, as you expand in Taylor series and then compute every term in this Taylor series expansion as an explicit matrix and sum up. And then the expression you will see, you will get will be as follows. So identity matrix multiplied by cosine theta over 2 plus I multiplied with sigma multiplied with n with sine theta over 2. So cosine theta over 2 multiplied with identity matrix plus 4x4 matrix given by sigma multiplied with unit vector n that specifies our rotation axis and multiply with sine theta over 2. Now, what is interesting about this formula? So this formula realizes in an explicit way a transformation by finite angle theta. So what is interesting about this formula is that if you make a rotation by angle 2 pi, so in fact that means that you make a rotation by 360 degrees, then because in this expression the arguments of half of the angles are involved, you see that this will be nothing else as minus s n multiplied by theta. So in other words, when you perform a full rotation by 2 pi, the spinner does not come to itself, but it changes the sign. So if you now consider the transformation of a spinner, that means that psi prime on x prime, upon performing such a transformation, will go to minus psi on x, but it does not return to itself. Well, the point x prime actually returns to itself because x prime transforms with the matrix lambda, and matrix lambda is a matrix which depends on angle theta in such a way that it is periodic upon rotation by 2 pi. And therefore, this expression means that after rotation by 2 pi, psi prime becomes equal to minus psi on x. You start from a point, you return to the same point upon the Lorentz transformation given by this three-dimensional rotation, but your wave function psi does not return to the same value, but it receives a minus sign. And this is a specific, this is a very important specific of this representation, which we call spinor representation. So spinors, upon rotation by 2 pi, do not return to themselves, but they receive the minus sign. So
Professor,
sometimes, yeah.
so isn't it like like an antiparticle, like something?
No.
It's
No.
like
It's what is called double in representation theory. This is something which is called as double valued representation. Double valued representation of the rotation group, of the rotation group. And this is a specific of this spinor representation. A spinor representation has a property of being double valued because now you are sitting in the one and the same space time point, but you can associate to your spinor either the value psi on x or the value minus psi on x. And then you see that under performing a loop in space and returning back to the original position, your spinor can change the sign. Your spinor changes the sign, actually. Yes, that's what you see from this transformation. So such representations, they have a specific name in representation theory. They are called double-valued representations of the rotation group. So rotation group is SO3. SO3 has a topological property of being not simply connected. So SO3, if you try to draw it from a topological point of view, it looks like a circle. So it is connected, but it's not simply connected. It's not simply connected means that there are loops in SO3 that are not contractible to an identity. So such loops which are not contractible to the identity mean that the corresponding space is not simply connected. So SO3 is not simply connected, and as such, it has a special class of representations which are not single-valued but double-valued. Double-valued representations, and we have already discussed this, I think, when we were discussing the relation between SO3 and Lorentz group realized as SL2C. SL2C is a double cover of the Lorentz group. So SO3 has a double cover. It can be covered in such a way. Let me draw it this way. Meaning that at each point of SO3, you have two values of another group, which is called a double cover of SO3. And it turns out that this double cover of SO3 is what we know as SU2. And SU2, group SU2. So SU2 is a double cover of SO3. Double cover is simply connected, while SO3 is not. And this topological property of being not simply connected, as I mentioned, leads to the existence of a special class of representations, which are called either spinor representations or double-valued representations of this rotation group. In fact, this also means something else. This means that you cannot observe the spinor itself. So spinor psion x itself is not an observable, is not a good observable. Because if you are an observer and you perform a transformation of the Lorentz frame by 2 pi, so in fact you return back to the original point by making a loop in space, if psion x would be an observable, then it would be something strange. You will see that doing nothing, returning to the same point, suddenly the components of your observable change the sign to the opposite. That would be, of course, unacceptable. And this means that psion x cannot be observed. But what can be observed is the quadratic combinations, for instance, quadratic combinations of spinor components. Some quantities like psi bar psi, for instance. So these quantities are quadratic in psi, and these quantities remain invariant upon making the rotation in space, upon making a loop in space. Such quantities would be invariant, and such quantities then provide observables, but not the components of the spinor itself. Yes, for this property of changing sign upon making a loop in space.
It's similar to the in Mobius strip. Where do you see?
Well, Möbius strip is demonstrating some other property, namely it's a surface with just one side. So yes, one side surface. Here it's a bit different. Here it is what I'm saying is related to the fact that the group SO3 itself is not simply connected. That's essentially what's happening here. And as a result, it has this property of having this particular class of spinor representations, which are double valued, but they are single valued for the universal cover of the group SO3, which is SU2. And we come back to this a little bit later. I think it will be clarified a little bit later. Now, in the Dirac,
I have
yeah,
another question maybe. So
sure.
for SO3, we have two different representations. First one is the vector representation, and this double valued representation. So the question is, if there exists some other, are they the only two, or do you have some other representation?
No, there are other representations as well. Actually, representations of SU2 or SO3 parameterized or classified by given half integer number. So I think you know this. If you think about this and you remember the construction of the representation of SO3, then you remember that every representation is characterized by a quantity which is called spin. Spin can take half integer values. So half integer values. Which are 0, 1/2, 1, 3/2, and so on. And any representation of a given spin has 2j+1 components. The dimension of a vector space on which this representation acts is a space of dimension 2j+1. Remember? 2j+1. So for instance, for the case of spin 0, you have just one component, and this is a scalar. For the case of 1/2, if you plug in this formula 1/2, you will have two components. And although our representation here is realized on 4-dimensional spinors, what we also see is the following. So if I compute explicitly what sigma I is in the Dirac representation, so take Dirac realization of gamma matrices in terms of Pauli matrices, then computing sigma I, you will find out that this is given by sigma I, and here there will be zeros. So it's a diagonal expression in terms of Pauli matrices. And then with this explicit form of sigma I, you see that the formula, which I have written here, in terms of this sigma capital, or if you wish, in terms of this explicit expression, then this formula further specifies and can be written in the following way. So this matrix S also becomes block diagonal, where here you have 2 by 2 0 blocks, and here you have identity, 2 by 2 identity matrix multiplied by cosine theta over 2 plus I Pauli matrix sigma multiplied by n sine theta over 2, and here analogously 1 cosine theta over 2 plus I sigma multiplied by n sine theta over 2, like this. And so you see that if you 4-component spinor is represented in terms of two-component spinors, so you write it as like phi and chi, where each of these is a 2-component spinor. So 2-component. Then these 2 components transform independently with respect to 3-dimensional rotations. And moreover, they transform in the same way. They transform absolutely in the same way. And that is exactly the representation of spin 1/2, which I have mentioned. Spin 1/2 realized explicitly by means of the following 2x2 matrices. Identity multiplied by cosine theta over 2 plus I sigma n multiplied by sine theta over 2. So it's a realization of rotations by means of 2x2 matrices. Rotation realized by 2x2 matrices, and this is the same as representation of spin 1/2. But in fact, you can build up representation corresponding to any half integer spin, integer or half integer spin. So either 0, 1/2, 1, 3 over 2, and so on. So in particular, vector representation is a three-dimensional representation. So 2j plus 1 is equal to 1, and it corresponds to vector representation. So this is vector representation. This is trivial or scalar representation. So trivial, and this is spinor. So the next spinor representation will be representation of spin 3 over 2. Okay, that is how it looks like.
Yes, so for the representation for spin 3 over 2, the matrix, gamma matrix should be different from the...
Of course, yes. And matrix which would realize this representation must be a matrix 2, 3 over 2 plus 1. It must be 4-dimensional. So this is equals to 4. Must be 4x4 matrix. 4x4 matrix. We also have here realization of rotations on 4-dimensional spinors by 4x4 matrices. But we see, in fact, that this representation factorizes into diagonal blocks. And so you see then you can reduce it to transformations on two-component spinors, which do not mix with each other. So they transform completely independently for the reason that here you have just 0 blocks. So this phi and chi do not mix at all. And so that means that you can restrict your representation just to phi or just to chi, where on these spinors it acts in the same way. So in fact, we can say that our 4-dimensional representation just breaks into two representations on this for these two-component spinors, and each of them is just a representation of spin 1/2, realized by 2x2 matrices. And when I'm talking about this classification of representations of spin characterized by spin, I'm talking about what is called irreducible representations. So in other words, representations which cannot be decomposed further. They do not have inside themselves invariant subspaces, so you can decompose them further on smaller irreducible components, smaller components. This is not possible. I'm talking about so-called irreducible representations which cannot be further reduced. And this classification of irreducible representations of the rotation group tells us that any such representation is uniquely characterized, uniquely up to unitary equivalence to be exact, is characterized by a half integer number, which is called spin. And if you fix this number, then the dimension in which you realize this representation is related to spin by the formula 2j plus 1. This will be a representation realized by matrices of dimension 2j plus 1 cross 2j plus 1.
Okay. So here the matrix you wrote as n theta is not irreducible. It is reducible, right?
Yes, so in this case, we obtain a representation which is from the point of view of reducibility is reducible, and is reducible with respect to SO3, and the irreducible components are given by this two-dimensional spinors phi and chi, which realize, yes, irreducible two-dimensional representations of the rotation group. Indeed.
Okay, thank you.
So once again, every reducible representation in representation theory, sometimes they are called DJ, is parameterized by half integer number j, called spin, and the dimension of this representation dj for a given spin j is equal to 2j plus 1. And that is what we explicitly see for the case of j is equal to 1/2. So
for because this is a spin half particle here, so that's why we have two irreducible representations.
Yes, we have two irreducible representations, and we have now actually to investigate what actually happens when I consider also Lorentz boosts. So far we restrict ourselves just to rotations, but this is not the whole Lorentz group. The Lorentz group also includes Lorentz boosts. And so the question is what happens, for instance, with our two components phi and chi under Lorentz boosts. Okay.
So if we have, like, for example, 3/2 spin, so will we have some 4 irreducible representation? Or
sorry, if you say we have 4.
If we have spin like 3/2, then how many
3/2, then it will be
representations?
reducible. No, the spin.
Yeah,
If you talk about spin 3/2, then our general theory is telling us that this representation has dimension 4. So representation will be realized by 4x4 matrices, but this representation will be different from what we are discussing now. Our representation here is also given by 4x4 matrices, but it is reducible because secretly we understand now that these are two irreducible representations of spin 1/2. Representation of 3/2 with spin 3/2 will be irreducible, and we will not be able to split our spinor into two components. These two components, if we make such a split, they will be transforming via each other under representation with the spins 3/2. We will not be able to decouple phi from chi. It would be different representation, not the one which we are considering here.
So
okay?
It is itself an irreducible.
This one is reducible.
Yeah, for 3/2, as I'm saying.
3/2 is irreducible. So my classification here is a classification of irreducible representation. This is important to have in mind, that this gives a classification of irreducible representations. Representations which cannot be reduced. And reducibility means that you don't have invariant subspaces. Subspaces in your representation which are invariant with respect to the action of the group elements, of all the group elements. If you have a subspace in your representation space which is invariant under the action of your group, so you pick up a vector, you pick up an element from your subspace, and then all group elements acting on it will not take it out of your subspace, then it means that your representation is reducible because you can reduce it. You can reduce the space to a subspace, which is closed under the action of your group. And what we are talking about here, this is a classification of irreducible representations. In other words, representations which do not have inside invariant subspaces. And so in this way, they cannot be reduced any further. They are already irreducible. Okay, and this is exactly the classification I'm talking about here. It's a classification of irreducible representations.
All right, I have another maybe stupid question. So here, why don't you just use a irreducible representation for spin 1/2 here with some 2 by 2
That's
matrix?
because, yeah, that's a good question. That's a good question. We don't use it. We actually talk about this, but because we are talking about representations of the Lorentz group. So what we are saying now is that we are looking at the representation of a bigger group, not only about the rotation group, but we are talking about representation of the Lorentz group, which is bigger than the rotation group. Now we see that if representation which we have constructed of the Lorentz group, if we restrict it to the rotation group, then this representation is indeed reducible, and it has 2 irreducible components of spin corresponding to spinors, 2-dimensional spinors of spin 1/2. But our group is bigger. Our group is proper orthochronous Lorentz group plus also discrete operations of parity and time reversal, which all together make the full Lorentz group. And so relativity principle is telling us that the Dirac equation must be covariant with respect to the full Lorentz group. And so we have to answer the question actually about all possible transformations in the full Lorentz group. That includes transformations from the proper Lorentz group and the discrete operations of parity and time reversal, and in turn, transformations with respect to the proper orthochronous Lorentz group have inside rotations, the subgroup of rotations. And now what we are doing here is we are zooming on this smaller rotation group, and with respect to this group, we see that our 4-dimensional Lorentz transformations is reducible, and it decomposes into 2 irreducible components corresponding to this 2-dimensional spinors, realizing representation of SO3 of spin 1/2.
Okay, so the classification of irreducibility is only for the rotation?
No,
SO3.
no, it is also for Lorentz group, and we will see it now, because now I have to also tell you something about boosts.
Okay.
Yeah, so we are going to consider the boosts. So Lorentz boosts. Lorentz boosts. That's the whole story is very interesting, and after I will give you this formal construction, we have to discuss it. That is very interesting how things are working here. So for Lorentz boosts, we have omega 0I given by the formula Ni. So again, rotation axis. Multiply with hyperbolic angle, which I call var theta. And then this matrix of Lorentz boosts Sn var theta is given by exponential 1/2 gamma 0 gamma I Ni var theta, which is the same as exponential 1/2. And then you recall that gamma 0 gamma I is nothing else as an original matrix alpha alpha I, which I have introduced discussing the Dirac equation. So you have 1/2 alpha, and then alpha I and I you can write as a concise product of two vectors, alpha and n, where alpha in fact is a triple of matrices multiplied by var theta. And this again you can explicitly compute and find the following expression: 1 multiplied by hyperbolic cosine, so cos, var theta divided by 2, plus alpha multiplied with n, and sinh var theta over 2. So the fact that we are dealing with Lorentz Boosts now shows itself in the appearance of these hyperbolic functions, signaling that you are dealing now with Lorentz Boosts. And this is how this transformation looks like. Now, since in the Dirac representation, matrices alpha I are block of diagonal, this spinors phi and chi, these two-dimensional spinors which I introduced above, they mix under Lorentz Boosts. You see, they mix under Lorentz Boosts because explicitly matrices alpha I, recall, they are given by sigma I 0. So they are exactly off diagonal. And as a result, when you compute this matrix explicitly, you see that this matrix will mix the phi and the chi. So in this Dirac representation of gamma matrices, phi and chi mix, and by themselves, they are not relativistic covariant. They are not relativistic covariant. You cannot, in this representation, to restrict yourself either to chi over phi, because there is a mixing. But we come back to this question of mixing in a moment. Let me also mention the hermeticity properties of these transformations, Lorentz transformations we found. Yeah, so for space rotations, we see that if you take S dagger, so compute the Hermitian conjugate of matrix S, then this is exponential 1/2, and then you have some I is less than J, gamma I dagger, gamma J dagger. Actually, upon dagger, you have to change their order because these are matrices, and under Hermitian conjugation matrices change their order, multiplied by omega ij. Omega ij is real, so they are real numbers. And now using the fact that this matrix is gamma I Hermitian, Hermitian, anti-Hermitian, then this is the same thing as 1/2 I less than J, gamma J, gamma I, omega ij. So minuses cancel because they appear twice. You have two gamma matrices, so then minuses cancel. And then if you put these matrices in the old order by anti-commuting them, you will get the minus sign here. And as a result, you see that what you obtain here is the same matrix S, but with a minus sign in the exponent. And so this is nothing as S minus 1. So S dagger is equal to S minus 1, or in other words, what you find is S dagger S is equal to 1. And obviously, we call such matrices unitary. unitary. And so we see that our rotations are realized by unitary matrices, or in other words, we are realizing a unitary representation of the rotation group. So F realizes unitary representation of the rotation group. What about Lorentz boosts? For Lorentz boosts, we have S dagger equals to exponential of 1/2, again, gamma I dagger, gamma 0 dagger. So I change the position of gamma matrices, the order of gamma matrices. And then I know that gamma I is anti-Hermitian, gamma 0 is Hermitian. So I get minus 1/2 gamma I, gamma 0, omega 0I. Then I anti-commute matrices gamma I, gamma 0 by using the Clifford algebra. So I will get 1/2 gamma 0, gamma I, omega 0I. From where you see that what I have obtained is the matrix S itself. So this is different from the unitarity condition. Rather, this condition shows that matrix S realizing Lorentz boosts is Hermitian. So S is Hermitian, not unitary, but Hermitian. Not unitary, but Hermitian. And in fact, both properties under Hermitian conjugation, I mean, both by both, I mean rotation matrices, behavior of rotation matrices and behavior of Lorentz boosts under conjugation can be combined in one formula, which looks as follows. So S dagger is equal to gamma 0, S minus 1, gamma 0. When you consider rotations, then you can see that actually gamma 0 commutes through matrix S and gamma 0 squared is 1. So S dagger is equal to S minus 1 and matrix S is unitary. And on the other hand, if S is a Lorentz boosts, then as gamma 0 anti-commutes with gamma I standing in the exponential, and for this reason you will get minus sign, and S minus 1 will turn into S, and you get the Hermitian condition for matrix S corresponding to Lorentz boosts. But both together, these hermiticity properties are encoded in one formula, which looks like this. And in fact, this formula motivates to introduce the notion of a Dirac conjugate spinor. So Dirac conjugate spinor is defined as follows. It's denoted by psi bar, psi with bar. I think I already used this expression, but now I give a motivation why it is introduced. Given explicitly by psi conjugate transpose, which means psi Hermitian conjugated, multiplied with matrix gamma 0 from the right. So this psi bar constructed in this way is not a column, but this is a row. Row consisting of 4 numbers, which you can also write, as I said, as psi dagger, which means conjugation and transposition multiplied with gamma 0. And this is because this spinor psi bar has a simple transformation property under Lorentz transformation. So psi bar or bar on psi prime x prime transforms as S psi. So I'm transforming psi, then I take complex conjugate and transposition, multiply with gamma 0, which is, according to our discussion, the same as dega. And so I get psi dega as dega gamma 0. And in all cases, as dega is given by this formula here, so I get psi dega gamma 0 as minus 1 gamma 0. Multiply with gamma 0, but gamma 0 squared is 1. So and here is psi bar again. So this is psi bar on x multiplied with s minus 1. So in other words, under Lorentz transformations, this Dirac conjugate spinor transforms simply by multiplying it from the right, because it is raw, by the matrix S minus 1, which is compatible actually with the Dirac equation now written in the following form. Psi bar, so Dirac equation inherited by this Dirac conjugate spinor, which looks like this: I gamma mu d mu plus mc over h bar equals to 0, where now this derivative is understood as acting on the left, acting on psi bar. And sometimes, in order to emphasize this fact that d mu acts to the left, but this is obvious because there is nothing on the right to act, so it must act to the left. This is indicated by putting arrow indicating to where this derivative acts. So this is a Dirac equation for the Dirac conjugate spinor. Dirac equation to which this Dirac conjugate spinor satisfies. For Dirac conjugate spinor conjugate. It follows, of course, from the original Dirac equation by taking conjugation of the original Dirac equation and multiplying it with gamma 0, then you can derive this equation from the original Dirac equation. Dirac equation for Dirac conjugate follows from the original Dirac equation. And then you can independently check, of course, that this equation for the Dirac conjugate spinor remains to be Lorentz covariant, exactly due to the properties that under Lorentz transformations, this Dirac conjugate spinor transforms by multiplying with matrix S minus 1 from the right. Okay, now, so we considered the transformation properties of our spinors with respect to the rotation group and with respect to Lorentz boosts, which altogether provide the realization of the proper orthochronous Lorentz transformations. And we did it in the Dirac representation of gamma matrices. And in this Dirac representation for gamma matrices, we have seen that rotation group is realized in the form of a reducible representation, which splits into two irreducible two-dimensional representations, while Lorentz boosts mix these two-dimensional representations between themselves. And now I would like to talk about discrete transformations which are left over. And they have to be taken into account if we want to talk about the full Lorentz group. So we have to realize how our spinors transform under parity and under time reversal. So parity and time reversal. So let's start from parity. So parity. So concerning parity, I mean, considerations are very similar. So parity, what is this? This is an operation which takes three-dimensional x and sends it to minus x, and does not do anything with time. So time remains unchanged, while coordinate x's are reflected. All three coordinate x's are reflected. So this means that x prime is equal to minus x, and t prime is equal to t under this transformation. And then again, we are looking for psi prime on x prime, transformed psi in the new Lorentz frame obtained from the old one by means of this parity transformation as some matrix, I call it P capital, multiply with psi on x. And I want to find this matrix P, which leaves my Dirac equation to be covariant. Now, then this is very simple. You just look at the Dirac equation again, I gamma mu d mu minus m acting on psi, and then this must be looking the same in the new frame, so psi prime on x prime. Then you see from here that if you write it in terms of gamma I gamma 0 d0, then this term will not be changed because time is not changing under this transformation, while the derivative with respect to x prime you can write as an all derivative, all spatial derivatives d over dxi, but you put minus sign because x prime is equal to minus x. So derivative with respect to x prime is equal to minus derivative with respect to x. Then there is a mass term, and then psi prime on x prime will be psi prime on x prime, which you write as matrix P psi on x, and this must be equal to 0. So this is how your Dirac equation looks like. From where you actually see that if you multiply this equation with p minus 1 from the left, then to get the original Dirac equation, you need to satisfy the following conditions: p minus 1 gamma 0 p, it's not writing. Must be equal to gamma 0. So gamma 0 must stay invariant, while p minus 1 gamma I p must gives me minus gamma I to compensate this minus here. So if I will find the matrix P which satisfies this condition, then I will find how my spinor will be transforming under parity transformation. And you see actually that these equations can be elementary solved if you pick up matrix P to be proportional to gamma 0, and some proportionality coefficient I denote by eta with a subscript P, multiply with gamma 0. So gamma 0 will commute with gamma 0, so the first equation is trivially satisfied. And then we know that gamma 0 is anti-commuting with gamma i's, and so then the second equation will be satisfied. And since I'm taking p and p minus 1, then this prefactor, which is a number, eta p, called internal parity, will be satisfied. So this number eta p is called internal parity. And this transformation P we can require to be a unitary operator. So it is a unitary matrix satisfying the condition P dagger P is equal to 1, which means that this number eta P must be a phase. So it must have a modulus equal to 1. And then you might also require that if you perform parity twice, so you return back to the original point. So you first reflect all the coordinate axes, and then you reflect them back. So you return to the original situation. Then you may impose the condition that square of parity is equal to 1, is equal to the identity matrix. So nothing happens if you apply the parity transformation twice. But on the other hand, you know that you are dealing with a spinor, and actually you might, in this case, say that after application of parity twice, you are not returning to itself, but you're returning to itself up to a minus sign. And so in the second situation, you can require then P squared squares P squares to -1, minus identity matrix. And so in the first case, for internal parity, you will find just these numbers eta P is equal to ±1, while in the second case, you will find that this is ±I, right? ±I if you apply this parity twice, because these formulas are based on the statement that gamma 0 squared is equal to 1. So if you will use a P here and here or here, you will then identify an internal parity either as ±1 or ±I. You can also find out that P anti-commutes with gamma 5. So if you take P -1 gamma 5 P here, then this is P -1, and then gamma 5 is I, gamma 0, gamma 1, gamma 2, gamma 3, and P. And then P is proportional to gamma 0, and you need to move gamma 0 through all these gamma matrices. And gamma 0 anti-commutes with gamma 0, gamma 1, gamma 2, gamma 3, but commutes with itself. And so as a result, you will have here minus gamma 5. So parity, matrix realizing parity anti-commutes with gamma 5. And so if you take now two-component spinor, phi, four-component spinor, but written in terms of these two-component spinors, so phi and chi, and act with this parity operation on it, this is then eta P internal parity multiplied by gamma 0 acting on phi chi. And in the Dirac representation, you see then this is nothing else as eta P phi minus eta P chi. So parity acts in such a way that it preserves two-component spinors. They do not mix. But you see from this computation that these components have a different parity. So phi goes to 5 up to this eta P, but component chi receives this extra minus sign. So these components in this situation, in this way, you can say that have an opposite parity. So parity is opposite. Parity is opposite. Now, you can pick up, of course, there is a question, what you have to pick up for an internal parity, either ±1 or ±I. And simply you can see that the notion of parity must be defined in the same way for all spinors. You can pick up parity to be equal plus minus 1, or you can pick it plus minus I, does not matter. What matters is that you pick it once forever, once for all the spinors, So you can fix this number eta p to be the one and the same for all the spinors. And then it will be a consistent choice for your theory. Otherwise, it is up to the freedom. Parity transformations are defined up to the freedom, which I mentioned here, in terms of this phase eta p, which can be either plus minus 1 or plus minus I. Now, if we make this choice for all the spinors, the one and the same, of this internal parity, then with respect to the parity, you can see, you can actually classify the bilinear combinations of spinors in the following way. So you see that first of all, you have an object psi bar psi. So this is the multiplication or scalar product of the Dirac conjugate spinor with the spinor itself. And so you multiply rho with the column, and so you get a number. So this psi bar psi is a number. And under Lorentz transformations, you see that psi bar transforms with s minus 1, while psi transforms with s. And so s minus 1 and s cancel each other. And so this object here transforms as a scalar. So this object is a scalar under Lorentz transformations. Then we can have an object which is psi bar gamma 5 psi. And then you see that under Lorentz transformations, because Lorentz transformations anti-commute with matrix gamma 5, that is something which I have already mentioned, right? So that Lorentz transformations do they anti-commute with matrix gamma 5, then this object appears to be a pseudoscalar, is what is called pseudoscalar. And you also see that this object it goes to minus itself under parity transformation, exactly due to this property that under parity gamma 5 goes to minus gamma 5. Then you have an object which transforms under Lorentz transformation as a vector. This is psi bar gamma mu psi. That is very important combination. It's a current, which is, it has this dependence on the index mu. So this is a vector under Lorentz transformations. Then you might have a pseudo vector, which is psi bar gamma mu gamma 5 psi, pseudo vector. So it transforms as a usual vector with respect to Lorentz transformations from proper-synchronous Lorentz group, but it changes sign under parity. So it's a pseudo vector. It behaves itself as a pseudo vector. What else? What else? I should say it's other way around. So the usual vector would change the sign under parity transformation because it's a vector. So when I do a transformation x to minus x, the vector should, or I reflect, if you wish, coordinate axis, then a vector must change the sign. While a pseudo vector does not do that. So pseudo vector, for an example, if you have two vectors and you take a vector product of two vectors, then you get a pseudo vector, as you know very well, because this object will not change the sign under the reflection of the coordinate axis. And so that's exactly as this bilinear combination psi bar gamma mu gamma 5 psi behaves itself. It behaves itself as a pseudo vector. Now, and finally, we can have an object which is bilinear combination of our spinors as psi bar sigma mu psi, where sigma mu was that antisymmetric tensor I introduced among 16 possible matrices which we can construct from our gamma matrices. And then this object, you can see that this object transforms as an antisymmetric tensor. Symmetric tensor. So in fact, here, as you can see, I've used my 16 independent matrices, which I can construct from gamma matrices to build up the corresponding bilinear combination of spinors. And then knowing how spinors transform under parity under Lorentz transformations, you can see the classification of the corresponding bilinear combinations in terms of their transformation properties. Like, for instance, psi bar psi you made out of your spinors will be a scalar. Psi bar gamma phi psi will be a pseudo-scalar. So this is object which changes the sign under the reflection of coordinate axis. Psi bar gamma mu psi will be a vector, also an object which will change the sign under the change of under reflection of the coordinate axis. Then you have a pseudo vector, the object which does not change the sign, so it's like behaves itself like a vector product of two usual vectors. And psi bar sigma mu psi, this object will transform under Lorentz transformations, including parity, as an antisymmetric tensor. Okay, good. I think for today my time is up. So I have to finish with a time reversal. Time reversal is understood exactly, should be understood exactly in the same way as we did for parity. And then I will discuss a very important topic, which is related to the notion of while spinors. While spinors. Okay, if you have questions, I'm ready to answer.
Professor,
Mm-hmm.
this transformation of the spinor on the parity that has different signs, this has some physical interpretation related with the system of antiparticles or something.
Yes, so you can relate. Well, about antiparticles, we can talk. So first of all, we have to understand what antiparticles are. So let's postpone this discussion till I will tell you what antiparticles are. Then it will become more clear. Actually, to discuss particles versus antiparticles, I have to introduce one more important discrete operation which acts on spinors, and this is operation called charge conjugation. Okay?
Okay.
Operation charge conjugation, and this is something which will be distinguishing for us particles from antiparticles, and this will be important. So let's postpone this discussion until we give a definition what we mean by antiparticle, okay?
Perfect, okay.
That involves this notion of charge conjugation, which we need to discuss first. Okay.
So maybe
Yeah, sure.
ask again my previous question. So we discussed that for rotation, the representation is reducible for a spinor, but
Yes.
the Lorentz boost, it meets the two components. So can we say that if we're considering the whole Lorentz transformations, this 4x4 matrix representation is irreducible for a spinor?
We will find out. This is sophisticated. That's a bit sophisticated. And that is also something which I want to postpone till the discussion of while spinors, because we will see that in spite of the fact that we have observed that under Lorentz Boosts our spinors phi and chi mix. Yes, that's what we have observed.
Yes.
I will show you that this mixing is an artifact of our use of the particular Dirac representation. And in fact, it turns out that the representation of the proper orthochronous Lorentz group, which we are dealing with here, is in fact also reducible. And going to another representation for gamma matrices, you can make this statement very explicit. So I will change a representation of gamma matrices, going to the so-called Weyl representation, where it turns out that both rotations and Lorentz transformations act in such a way that the two components spinors, phi and chi, do not mix. So in fact, the whole proper orthochronous Lorentz group realizes a reducible representation in this case. And in fact, it's better to say more exactly, exactly to say is that what happens is that four-dimensional representation of the proper orthochronous Lorentz group will split into two irreducible two-dimensional representations of the Lorentz group, and these two representations will be non-equivalent. They will not be related to each other by a unitary transformation or simply by a similarity transformation.
Oh, that sounds interesting. So we will discuss this next lecture.
Yes. We will discuss it next time. What we will also see that in spite of the fact that the representation of the proper orthochronous Lorentz group will be reducible, the parity will still mix the components and break this irreducibility. So representation of the full Lorentz group, including parity, will be irreducible.
Mm-hmm.
The proper orthochronous Lorentz group will act reducibly, but parity, if we extend it by adding up parity, then parity will not keep this property. And that's why two spinors, which transforms nicely and independently with respect to each other, with respect to proper orthochronous Lorentz group, will turn out to go into each other under parity transformation. But I will show you all these features explicitly next time.
Okay, I see.
I will derive this property. I will derive these properties. You will see them in an explicit way. And then we come to discuss this important important transformation, which is called charge conjugation. That's, of course, very important. That is exactly what was so fascinating about the Dirac equation, is the prediction of antiparticles. That with every particle, you also have an antiparticle. And you will see that charge conjugation is simply a symmetry of the Dirac equation, a new symmetry of the Dirac equation, hidden in this equation. Okay, so Dirac equation is a completely fascinating object, a completely fascinating thing. And I, of course, welcome you in many ways to study it as much as possible. Okay, if you don't have any further questions, then I wish you a pleasant day, and we hear each other next Friday to clarify all these interesting questions.